Hello students, I am Dr. Shilpa K. Godar, Associate Professor, Department of ECE, SJBIT. Today I am going to explain some topics related to basic electronics. So first we will start with here Zener diodes. So Zener diode in the sense here it is also sometimes called the breakdown diode. It is a PN junction diode specially designed for operation in the breakdown region in reverse bias condition. Construction and working of Zener diode is like an ordinary PN junction diode except that it is properly doped so as to have a sharp breakdown voltage. The diode may use either Zener breakdown mechanism or avalanche breakdown mechanism. Despite the fact that the avalanche and Zener constitute two types of breakdown diodes, the name Zener is commonly applied to both types of diodes. The breakdown diode may be silicon or germanium one, but silicon is preferred over germanium because of a higher operating temperature and current capability. The key point is also more sharp in case of silicon diode. These diodes are analogous to gas discharge tubes in which large current appears on reaching the breakdown potential. Next, this is the characteristics and parameters. So here Zener diode. It is a two-terminal device and the terminals are anode and cathode. So which is shown in this figure. Next, we will find here structure of a diode as well as the structure of a this is a structure of a Zener diode. Next, equivalent circuit. So first we will check it the biasing of a Zener diode as well as the VI characteristics of a Zener diode. So first we will consider forward biasing of a Zener diode. So where the anode of the Zener diode is connected to the positive terminal of the DC source and the cathode is connected to the negative terminal, then the Zener is said to be forward biased. The forward biased Zener diode behaves identical to a forward biased diode. So, the forward characteristics of a Zener diode is shown in this figure. It is almost identical to the forward characteristics of a PN junction diode. Next, we consider the reverse biasing of a Zener diode. So, in this, when the cathode is connected to the positive terminal and the anode is connected to the negative terminal of the DC source. The Zener diode is said to be reverse biased. The operation of Zener diode in the reverse bias condition is substantially different from that of a diode. Next, reverse characteristics of a Zener diode. It is shown in the above figure here. In this, the reverse characteristics of a Zener diode, it is substantially different from that of the PN junction diode. As we increase the reverse voltage, initially a small reverse saturation current I0, which is in milliamps, will flow. This current flows due to the thermally generated minority carriers. At a certain value of reverse voltage, the reverse current will increase suddenly. This is an indication that the breakdown has occurred. This breakdown voltage is called as a Zener breakdown voltage or Zener voltage, or it is denoted by Vz. The value of Vz can be precisely controlled by controlling the doping levels P and N regions at the time of manufacturing a Zener diode. After breakdown has occurred, the voltage across Zener diode remains constant equal to Vz. Any increase in the source voltage will result in the increase in reverse Zener current. The Zener current after the reverse breakdown must be controlled by connecting a resistor R. This is essential to avoid any damage to device due to excess heating. After a reverse breakdown, the Zener diode operates in a region called Zener region. In this region, the voltage across a Zener diode remains constant, but current changes depending on the supply voltage. So the above figure shows the VI characteristics of a Zener diode. where Vz will be equals to a Zener breakdown voltage, Iz minimum will be the minimum reverse current to sustain breakdown, and Iz maximum will be equals to maximum Zener current limited by the maximum power dissipation. So next, so this is also the Zener characteristics with enlarged view of a breakdown voltage. So next we have equivalent circuit or a symbol of a Zener diode. The equivalent circuit of a Zener diode, when it is operating in the Zener region of the reverse characteristics, is shown in the figure. The figure shows that the Zener diode is equivalent to a series combination of a small resistor Rz and a battery of terminal voltage Vz. Rz is called as the dynamic resistance of the Zener breakdown. Next, breakdown mechanisms in a Zener diode. In Zener diode, there are two types of different breakdown mechanisms. They are Zener breakdown and avalanche breakdown. Zener breakdown. So here the Zener breakdown is observed in the Zener diodes having Vz less than 5 volts or below 5 to 8 volts. Due to heavy doping in Zener, the depletion region at the junction is very narrow when the voltage across the junction is increased. The electric field across the depletion region becomes so high that the electrons are pulled out of the covalent bonds. This results in a sudden rise of a current. This is known as a Zener breakdown. Next we have avalanche breakdown. The avalanche breakdown is observed in the Zener diode having Vz higher than 8 volts. The acceleration of the electrons due to the external applied voltage gives high velocities. These fast electrons by collision produce further electrons. These electrons in turn get accelerated and liberated more electrons by collision. This process is called avalanche breakdown. This results in a sharp rise in a current. Next, application. So Zener diode as a voltage regulator. So that is an important application of a Zener diode is its use in voltage regulator. So that is Zener diode has voltage regulator. It is also called as shunt regulator. So here in the above figure, a current limiting resistor Rs is included in series with the source voltage Vi and the Zener diode to limit the current through the diode to a safe value. The maximum current in the circuit is given by Iz maximum will be equals to Pz by Vz, where Pz will be equals to power rating of the Zener and Vz will be Zener breakdown voltage. When the input voltage Vi is less than the Zener breakdown voltage Vz, the diode does not conduct and output follows the input. However, when the input voltage exceeds Vz, breakdown occurs and the voltage across the output remains constant at Vz. Next, we will consider here Zener regulator with no load. That is, when the reverse voltage applied to the Zener diode equals the breakdown voltage Vz. So Zener breakdown occurs and the Iz flows through it. So when we apply KVL to the loop here, Vi minus Iz into R1 minus Vz will be equals to 0. That is Iz will be equals to Vi minus Vz by R1 or R1 will be equals to Vi minus Vz by Iz. Minimum Zener current Iz minimum will be equals to Vi minimum minus Vz by R1 and maximum Zener current Iz maximum will be equals to Vi maximum minus Vz by R1 and power dissipated in R1 is given by PR1 will be equals to Iz square into R1. So next the advantages of Zener diode voltage regulators over other voltage regulators are they are small, lighter, more rugged and have a longer life. They are also simple and inherently cheaper. And some regulators have the following drawbacks. That is, their efficiency is low for heavy load currents because there is a considerable power loss in series resistor RS and the diode. The output voltage varies slightly due to Zener impedance RZ. The output voltage cannot be chosen independently but depends upon the breakdown voltage of the Zener diode. Thank you.